You pull out a tape measure, hook it onto the edge of something, and start measuring. But if you've ever looked closely at the end, you may have noticed something strange. The metal hook isn't firmly fixed in place. It actually slides back and forth. At first, that seems like a flaw. Shouldn't a measuring tool have a solid, unmoving starting point? Surprisingly, that little bit of movement is one of the smartest parts of the entire design. So why does the hook move? And how does it actually make measurements more accurate? Let's find out right here on History of Simple Things. The first time you notice the loose hook on a tape measure, it's easy to assume something is wrong. Maybe the screws have come loose or the tool has been dropped one too many times. But that movement is intentional. The metal piece at the end is called the hook, or sometimes the tang. It is designed to slide a small distance back and forth, usually by a fraction of an inch. That might seem like a terrible idea for a precision measuring instrument. After all, if the end moves, doesn't that mean your measurement could be wrong? Actually, the opposite is true. The movement is there because the tape measure is designed to be used in two different ways. Imagine you're measuring the length of a piece of wood. You place the hook over the edge of the board, then pull the tape away from it. As you pull, the hook moves outward, away from the tape blade. That movement is important because the hook itself has thickness. If the hook were completely rigid, the physical location where the tape blade begins wouldn't perfectly line up with the edge of the object you're measuring. The hook would effectively get in the way of the measurement. Instead, when you pull the tape, the hook slides outward by approximately its own thickness. This puts the tape's zero reference in the correct relationship to the edge of the object. In simple terms, the hook moves so that you don't have to mentally subtract the thickness of the metal. You're measuring the board, not the board plus the hook. This is why manufacturers call designs like this a true zero hook. The hook automatically compensates for itself. Now let's do the opposite. Suppose you're measuring the inside width of a window opening, cabinet, or doorway. This time, you can't hook the tape over an edge and pull. Instead, you push the end of the tape against one side of the opening and extend the blade toward the other side. As you push the hook against the surface, the hook slides inward, toward the tape blade. Again, that movement is deliberate. The hook has thickness, and if it stayed completely fixed, that thickness would interfere with the starting point of the measurement. By sliding inward by approximately the same amount as its own thickness, the hook compensates for itself. So the tape can give you the correct inside measurement without requiring you to add or subtract the thickness of the metal. Home Depot describes the same basic behavior. When hooking the tape over a board for an outside measurement, the hook slides away from the case. When pushing it against a surface for an inside measurement, the hook moves toward the case. Here's the problem the engineers had to solve. A tape measure needs to work accurately whether you're pulling it from an edge or pushing it against a surface. But the metal hook has physical thickness. If you made the hook completely rigid, you could make it accurate for one method of measurement, but the other method would introduce an error equal to the thickness of the hook. That might only be around 1/16 of an inch on a typical tape measure, but that can matter when you're doing precise work. Imagine measuring a piece of wood for a cabinet. You cut the wood based on your measurement, only to discover that it's slightly too long. You might blame your cutting, your reading of the markings, or even the wood itself. But a rigid hook could actually be part of the problem. The sliding hook eliminates that issue mechanically. Instead of asking the person using the tape to compensate for the hook, the tape measure compensates automatically. This is the really clever part. The hook doesn't simply move a little. Its design travel corresponds approximately to the thickness of the hook. That means the correction is built directly into the hardware. Pull the hook outward, and the measurement reference shifts one way. Push the hook inward, and it shifts the other way. The movement is small enough that you might never notice it during normal use, but it's large enough to compensate for the metal sitting at the very beginning of the tape. That's why trying to eliminate the movement by tightening the rivets is actually a bad idea. A properly functioning hook is supposed to have that controlled movement. Those little rivets at the end can make the hook look like it's loose or poorly attached, but they're doing something very specific. The hook is mounted through openings that allow it to move along the axis of the tape blade. The rivets keep the hook attached while still allowing that small amount of travel. So the hook isn't supposed to flop around in every direction, it's supposed to slide back and forth. There's an important difference. If your hook has a small amount of in and out movement, that's normal. If it's bent, stuck, badly worn, or moving excessively in other directions, that's another story. A damaged hook can affect the accuracy of the tape. You might wonder why manufacturers don't simply make the hook extremely thin. The answer is that the hook needs to be strong. It's constantly being pulled around the edges of boards, countertops, pipes, walls, and other materials. It also gets knocked around, dropped, and used thousands of times. Making it extremely thin could make it weaker and less practical. So instead, engineers kept the hook strong enough to do its job and gave it the ability to move. It's a much simpler solution. The hook can have the thickness it needs for strength while still allowing the tape measure to maintain an accurate 0 point. The next time you pick up a tape measure and notice that the hook wiggles, don't automatically assume it's broken. That movement is there for a reason. The hook is designed to move by approximately its own thickness, so the tape can produce accurate measurements whether you're pulling from an outside edge or pushing against an inside surface. It's simple, mechanical, and almost invisible during normal use, and that's what makes it so clever. Something that looks like a flaw is actually the feature that makes the whole measuring system work properly. Sometimes the smartest part of an everyday object is the part we barely notice. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.